Good evening and welcome everyone to week 2 of the NPTEL problem solving sessions for the course Introduction to Algorithms and Analysis. So in week 1 we saw like basics of computational complexity, how we calculated computational complexity for some simple algorithms like insertion sort, and we also learned how insertion sort works, how merge sort works, and some properties of uh, computational analysis, runtime computational analysis of algorithms. So this week the primary focus of the lectures was master theorem, right? So primarily this week professor focused on master theorem. So before taking any problems, I will just go through the master theorem here once again, just for the sake of completeness. So master theorem, it applies to recurrences, right, of the form a times t of n by b plus f of x, or we should, it's fine, we can write f of n also, because again we are talking about the runtime complexities here. And here a is greater than equal to 1, b is greater than equal to 1, and f is asymptotically positive, right? So whatever happens in the limit of n tending to infinity starting from 0, f remains positive. Okay, that is, these are the only requirements. So this is a recurrence. So basically the time complexity of the complete problem is defined in terms of the time complexity of the sub problem. So basically here we divide the problem into a smaller sub problems, right? And the f of n is basically the constant runtime, or basically the constant work that has to be performed for each sub problem. Okay, so we saw that there are three common cases of Master's theorem where we can basically use this to get the runtime complexity, right? So what we usually do in Master's theorem is basically we compare f of n with n times, n to the power of log a base b, right? So we compare f of n with this, and then we take the first case, that is if f of n is basically on the order of n log a base b minus some epsilon, right, for a constant positive epsilon. Okay, so if this is the case, then we can, so this is whole in power, right? So we can also write this as n to the power log a base b over n to the power epsilon. So for a positive epsilon, f of n grows by a, like, f of n grows slower than the original function that we compare it against, right, by a factor of slowly then n to the power log a base b by a factor of n to the power epsilon. Okay, so in this case, right, so for this particular case, when f of n grows slowly than the thing that we are comparing it against by a constant factor, right, like n to the power some constant, right? So in this case, the time complexity is a base b, right? So this is the first case. So this is when f of n grows slowly than n to the power log a to the base b, and the time complexity of the complete algorithm is of the order of n to the power log a base b, right? So the second case is when f of n is theta of n log a base b log to the power k of n. So in this particular case, f of n and n log a base b basically grow at similar rates, right? So there is not an order of difference. They are not the same, but they are similar, right? They are of basically the same order, the rate of change. So the solution in this case is basically when f of n and the function that we are comparing it against, basically n to the power log a base b, they are basically similar, then the runtime complexity is n log a base b log k plus 1 n, right? In the third case is when f of n is omega of n log a base b plus epsilon. So basically now f of n grows at a faster rate than n to the power log a base b, and here also epsilon is constant, right? So grows polynomially faster than n to the power log a base b by a factor of n to the power epsilon. Right, so if this is the case and f of n satisfies the regularity condition, right? So what is the regularity condition? That a times f of n over b is less than equal to c times f of n for some constant c less than 1. Right, so basically compared to the algorithm itself, the f of n should slow down basically. Okay, so it should basically be a converging series, not a diverging series, if time complexity was taken to be f of n, right? So in this case, the solution is basically the algorithm is of the order of f of n, right? So if f of n is growing faster, then of course f of n dominates the runtime of the complete algorithm, right? So now let's take some examples. So these examples are also there in the lecture notes, and I am keeping them like similar. Right, so the first one is, right, so all of them will be recursions, because again we are just practicing master theorem and it is applicable only for recursions. N by 2 plus n. So here f of n is n, right? And what is n to the power log a base b? It is n to the power log 4 base 2, basically n squared. So f of n grows slower than n squared, right? So this is basically case 1, right? So we know that for case 1 the runtime complexity is basically n to the power log a base b, so it is n squared, right? Similar to the function that we compare it against. Second, t of n is again 4 times t n by 2, but now f of n, the extra work that we do for every sub problem, is n squared. And we know from the problem above that n to the power log a base b is basically n squared. So, and f of n is also n squared. So f of n and this n to the power log a base b, they grow at similar rates because they are of the same order, right? So this again is case 2. right? And in case 2, we know that the time complexity is basically theta of n to the power log a base b log k plus 1 n, right? And k here was 0, right? Because our f of n was basically having log to the power 0 of n, right? So the time complexity for this is n squared log of n, right? So for any algorithm that has f of n squared and a and b as 4 and 2, so this will be the current time. Let us take one more problem that shows the third case, right? 4 times t n by 2 plus n cube, right? So f of n grows faster than this, right? Because this is n squared and f of n is n cubed. So this seems like case 3. Right? But what we need to check for is regularity condition, right? So regularity condition is a times f of n by b should be less than equal to c times f of n. Okay, so it is basically 4 times n by 2 cubed should be less than equal to c times n cube, right? And this is for z less than 1, right? So this is 4 n cube over 8 c n cube 2, so n cube over 2 c n cube. So here we can see that regularity condition holds for c less than half. So for any value of c that is less than half and of course greater than 0, this condition holds, regularity condition holds. So this, now we can say with surety that this is case 3, and in this case the runtime of the algorithm is basically the runtime of f of n, that is n cube in this case. So let us take one more problem, right? That is t of n is 4 times n by 2 plus n squared over log n. right? So here a equal to 4, b equal to 2, like the usual routine, right? So to the power log a base b is again n squared, but f of n this time is n squared over log n, right? So now f of n, we cannot say for sure that f of n um, grows slower than n squared, right, for basically all values of n, right? I mean, it is indeed positive for all integers n from 1 to infinity, but this is not polynomially slower than n squared, right? Because initially it is slower, but going forward it grows, right? So for all values of n, the behavior is not well defined. So in this case, the master's theorem does not apply, right? So these were some examples of master theorem. Let us take one more example, right? Let us take t of n equal to 2 times t of n over 4 plus n to the power of 0.51. Okay, so here a is 2, b is 4, so n to the power log a base b is n to the power log 2 base 4. So this is n to the power of 0.5, right? And f of n here is 0.51. Okay, so this we can write as n to the power 0.5 times n to the power 0.01, right? So this is similar to case 3, right, for epsilon 0.01, right? So this indeed grows faster than n to the power log a base b by a polynomial, a fractional polynomial given by n to the power of 0.01, right? So we need to check for regularity condition, right? Regularity condition is a times f of n over b should be less than equal to, so basically c less than 1 should exist for this inequality to hold, right? So 2 times n over 4 to the power 0.51 is less than equal to c times n over n to the power 0.51. 2 times 10 to the power 0.51 over 4 to the power 0.51 equal to c times 10 to the power. So 4 to the power of 0.5 is 2, right? But 4 to the power of 0.51 is a value greater than 2, right? Slightly greater than 2. So 2 over 4 to the power of 0.51 is indeed less than 1, right? So this implies that for c less than 2 over 4 to the power of 0.51 that we have established is less than 1, the regularity condition is satisfied. So it means that this is case 3 definitely, and we can write the time complexity as similar to the time complexity of f of n. Right? Let us take one more question. What is the time complexity of matrix multiplication using divide and conquer method? Right? So for matrix multiplication to be posed as a divide and conquer method, let's say we want to write something like this, right? So right, we calculate partitions of C using partitions of A and B. Right? So to do this, what we need to do, we need to calculate all these submatrices R, S, T, U, and they are R is this, S is this, D is CE plus DH, and U is CF plus DH, right? this should be dg cf plus dh, right? So to do this, right, what we are doing, we are decomposing original multiplication of n cross n matrix into eight multiplications of matrices of half the size, right? Assuming that these are square matrices and n are even, right? And 4 additions of the matrices of same size, right? So this is basically a recursion, right? Because then these 8 multiplications also have to be performed using this kind of decomposition. So the runtime is 8, runtime for a multiplication is runtime of 8 multiplications of n by 2 size plus runtime of 4 additions, right? So addition is order of n squared, right? So this is 4 times order of n squared, so of course we assume n to be much larger. Right, so this is a recursive form, right? And since this is a recursive form, we can try to use Master's theorem for this, right? So A is 8, B is 2, right? F of n is just, we know that it will be of the order of n squared, right? And that is what is important. So n to the power log A base B n cubed and f of n is n squared. So clearly f of n grows polynomially slower than n to the power log A base B with an epsilon of 1, right? So order of f of n is basically n to the power log A base B minus 1. Okay, so this is case 1 of Master's theorem. So clearly the runtime of matrix multiplication will be of the order of n cubed, right? It will be dominated by the recursion and not by the extra work during every subproblem in recursion. Let us also take a look at Strassen's matrix multiplication, right? So this thing that we discussed above is ordinary divide and conquer matrix multiplication that uses 8 multiplications, right? Recursive multiplications. In Strassen's algorithm, right, it uses 7 recursive multiplications instead of 8, right? And how does it do that? So for the same terminology that we use here for the same blocks or the same submatrices, Strassen defines P1 as A times F minus H, P2 as A plus B times H, P3 as C plus D times E, P4 as D times G minus E, P5 as A plus D times E plus H, P6 as B minus D times G plus H. So every term here contains only one multiplication, right? So, and above every term contained 2 multiplications. So total it was 8 multiplications, and here including P7 we have only yet performed 7 multiplications, right? And using these 7 quantities, we calculate R as P just using additions. So the term R is plus P6, P2 plus P6. S is P1 plus P2. T is P3 plus P4, and U is P5 plus P1 minus P3 minus P7, right? So if we have to see, so in total for every recursion step, right, there are 7 multiplications of matrices of size n by 2, and then there are 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 18 additions and subtractions of the matrices of same size, right? So again, this is of the order of n squared. So clearly we will start seeing the effects of the algorithm only when n is much greater than 18, and practically we see speed ups for n bigger than 30, right? But because there are only 7 multiplications instead of 8, right, so the recursion relation is 7 times t of n by 2 instead of 8 times, and then order of n squared, right? So log 7 base 2 n to the power 2.81, right? And f of n is n squared. So again, f of n grows slower than n to the power log a base b. So this is the case 1 of Master's theorem. Right, so the time complexity is n to the power 2.81, and of course for bigger values of n to the power 2.81 is much less than n to the power 3, right, for bigger values of n. And there are different problems also the same method of calculating the order of the formula, or if you have any formula in a recursive form and we want to get the order of the final expression of the formula, original formula, then even then Master's theorem can be used, and there are some examples discussed in the class for that, right? So remember that the runtime for Strassen's algorithm is of the order of n to the power 2.81, right? So now n has to be just an integer, right? And can be 2, 3, 4, anything, right? Preferably even. Let's take one more problem, right? Let Rn be the number of n-bit strings that do not contain two consecutive ones, right? What is the recurrence relation for Rn? Okay, so we want n-bit strings, right, that do not contain two consecutive ones, right? So let us start writing some of the sequences for different values of n, right? Valid 1-bit strings, so it's basically 0 or 1, right? There is no other unique option. Valid 2-bit strings, then it will be 0, 0, 0, 1, 1, 0, but not 1, 1, right? So there are 2 strings, then 3 strings. 0 0 1 0 1 0 1 0 0 1 0 1. Right, so these are all the 3-bit strings. So there are 5 such strings. Right, and if we keep on writing like this, we'll see that this follows the Fibonacci pattern, right? So basically we'll see that the number of strings for n-bit strings is basically number of strings for n-1 bit strings plus number of strings for n-2 bit strings, right? So now again, this is another recurrence relation, right? So it's helpful to pose solutions to some problem in form of recursion, so then we can solve them easily using computers. So I think this should be enough for today's session, and next week we'll discuss week 3 contents. So bye for now.